Today we are going to explore one of the most important theoretical results in calculus, which is the mean value theorem. To understand the intuition behind this theorem, imagine taking a road trip where you drive a distance of 100 miles in exactly 2 hours. Your average speed for the trip is 50 miles per hour. Because your speedometer changes continuously throughout the drive, you intuitively know that at least once during the trip, your speedometer must have pointed to exactly 50 miles per hour. You were going faster at some moments and slower at others, but you had to hit your exact average speed at least once. The mean value theorem proves this concept mathematically for continuous and differentiable functions. Formally stated, the mean value theorem says that if a function f of x is continuous on a closed interval from a to b and differentiable on the open interval from a to b, then there exists at least one number, c, inside that open interval where the phi derivative evaluated at c equals the average rate of change of the function over the entire interval. And now, in mathematical terms, the derivative f prime of c is equal to the fraction where the numerator is f of b minus f of a, and the denominator is b minus a geometrically. This means that the slope of the tangent line at some point c on the curve is completely parallel to the second line connecting the two endpoints of the function on that interval. Let us look at a concrete mathematical example to see how this works. Suppose we have the function f of x equals x squared defined on the closed interval from 0 to 2. First, let us calculate the average rate of change of this function over the interval. We evaluate the function at the right endpoint, giving f of 2 equals 2 squared, which is 4. We evaluate the function at the left endpoint, giving f of 0 equals 0 squared, which is 0. The average rate of change is the fraction 4 minus 0 divided by 2 minus 0, which simplifies to 4 divided by 2, or 2. Next, we find the derivative of our function. The derivative prime of x for x squared is 2 times x according to the mean value theorem. There must be some number c in the open interval from 0 to 2, where the derivative equals our average rate of change of 2. So we set our derivative expression 2 times c equal to 2, which gives us c equals 1. Finally, because the number 1 lies strictly between 0 and 2, it satisfies the mean value theorem, meaning that at x equals 1, the instantaneous slope of the curve is exactly equal to the average slope over the entire interval. Let us consider a second mathematical example with a different function. Suppose we have the function g of x equals x cubed minus x defined on the closed interval from 0 to 2. First, we compute the average rate of change over this interval. We evaluate g of 2, which is 2 cubed minus 2, equaling 8 minus 2, or 6. We evaluate g of 0, which is 0 cubed minus 0, equaling 0. The average rate of change is the fraction 6 minus 0 divided by 2 minus 0, which equals 6 divided by 2, or 3. Next, we find the derivative of our function. The derivative g prime of x for x cubed minus x is 3 times x squared minus 1. We set this derivative expression equal to our average rate of change of 3, giving us 3 times c squared minus 1 equals 3. Adding 1 to both sides gives 3 times c squared equals 4, and dividing by 3 gives c squared equals 4/3. Taking the square root, we get two values for c, which are the positive square root of 4/3 and the negative square root of 4/3. When we check which of these values lies within our open interval from 0 to 2, we find that the negative square root of 4/3 is outside the interval, but the positive square root of 4/3, which is approximately 1.1/5, 1/5, lies strictly inside the open interval from 0 to 2. Therefore, this value of c is our valid solution to the mean value theorem. Let us examine a third example to see how the mean value theorem can be used to prove inequality. Suppose we want to bound the difference between the sign of x and the sign of y for any two real numbers x and y. If we apply the mean value theorem to the sine function on the interval from x to y, the theorem tells us that the sine of y minus the sine of x divided by y minus x is equal to the derivative of sine evaluated at some point c, which is the cosine of c, because the absolute value of the cosine of c can never exceed 1. We know that the absolute value of the fraction sine of y minus sine of x divided by y minus x is less than or equal to 1. Multiplying both sides by the absolute value of y minus x gives us the powerful inequality where the absolute value of the sine of y minus the sine of x is less than or equal to the absolute value of y minus x. This demonstrates that the mean value theorem is not just an abstract geometric statement, but an essential analytical bridge connecting local rates of change to global behaviors of functions.